My name is Thomas Heckelei, Professor for Economic and Agricultural Policy at the University of Bonn. I'm part of the PhenoRob Excellence Cluster in core project 6 on impact and upscale. And I'm very happy I can contribute here to the DIGICROP 2020 conference with the keynote on impacts of robotics and sensing technologies for crop production, an economist perspective. So a lot of what I will be talking about is really with contributions here from the team in the core project 6. This is a bit of a reflection of where we are at different places here. I'm going to turn off the video panel so we can focus on the slides. So there's this promise that robotics and sensing technology may transform agriculture. And this idea that technology matters so much is sort of prominent in the literature. A recent Nature large-scale simulation studies looked at the planetary boundaries of our food system. And it looked at different environmental domains related to greenhouse gas emissions, cropland use, blue water, nitrogen applications, and phosphorus applications. And it looked at what are different mitigation options that on the path to 2050 would allow us to stay within the planetary boundaries. And the key message here is that technology, as you can see in these bars, next to flexitarian diets, plant-based diets, cutting the waste of the system in half, and in the context of a rather optimistic pathway with not too much population growth and good income development, that in this context, technology plays a big role for cropland use, nitrogen and phosphorus applications, so sort of the key areas of our robotics and sensing technology. Well, this technological progress would allow to produce the same output with less resources. It said differently, could feed a growing population without a proportional increase in the resource use, so it would increase the resource use efficiency. And even though this simulation study was about general technological development, robotics and sensing might actually be or is seen by others also as a key for a sustainable agricultural system in the future. So the question is, how fundamental or disruptive will this potentially transformative change of robotics and sensing technologies be? And let's look at similar situations in the past. Well, for a long time, looking over a really large period of time now, the agricultural land used per person, so what is needed to feed a person, did go down only gradually. So with the increased knowledge of how we can produce food. During that time, so medieval ages and then later, the total agricultural land use increased significantly, increased with the growing population. And then with the Industrial Revolution really picked up and the corresponding population growth to really unforeseen levels. Well, in the beginning of the Industrial Revolution, how much land we use per person did not change much, but it did change then with the Green Revolution. Improved modern breeding, the use of chemical inputs, fertilizer, and then later pesticides really let the yields go up, so that actually what is needed per person to feed a person went down. And this sort of not halted, but lowered the push towards always more land into agriculture. But it also came with an intensity of agricultural production that had environmental impacts escalated. And there are two dimensions here of environmental impacts. What is happening per hectare? The higher intensity, the use of chemical inputs creates problems here, and this is what we are mostly talking about. But there's also the issue of how much land do we use, and we cannot use for conservation or for natural vegetation, for natural biodiversity. So the intensity caused problems per hectare, but the resulting yield saved land. So the question is, what will robotics and sensing technologies do in the future? Is it possible to reduce the per hectare environmental footprint by keeping up the yield? That would bring us a big step. But what and how, if this will be possible, is really hard to assess at this point. The robotics, for example, and we see here a few spraying and weeding robots, they are at the experimental development stage. They show that they can fulfill the promise in an experimental setting for some crops, some situations, some soils, some context, but they are far away from implementation in the real world. Robotics is the one side, the sensing the other. To make the robots and the crop management fulfill the promise, we need information about the state of the soil, the state of the plants, and that at a high resolution, not of the general field, but single small area, single plants. Even this will allow, if delivered and learn from it, then to precisely manage in an automated fashion the agricultural crops. So when we put these things together, we might arrive at this idealistic version of a future farm that has smart tractors, drones collecting information, and indirectly steering fleets of agribots. And we have the farmer sitting here and processing that information, steering it from his computer. So one interesting thing here is about this vision is it says future farms small and smart. Is that where the technology will push the future farms? Will it work for small ones? Will it help to take away the pressure from the farm structural change that we have observed the last 100 years? Well, that depends on what the technology can deliver. And if there are not certain scale effects that will make it, again, as so many technologies in the past, working better for larger farms. Well, so we get a feeling for the possibility that robotics and sensing technology could have a big impact. And they could contribute to sustainability through the understanding of the state and the needs of the crops and soil at a high resolution, allow them to have the management precisely and timely, and reduce labor costs to automation, and because of the precision, use much less chemical inputs and have therefore a lower environmental footprint. And if that all works, the yields will not go down despite lower chemical intensity. But the what, when, where, and to what extent this is all possible is wide open. And we need to come up with smart ways to, think about this and analyze it, and also from the science point of view, shape, based on our understanding, the direction of development, but also the communication in the wider society. So the objectives of this talk, they are limited in the sense that we want to characterize what we know and do not know about the adoption of robotics and sensing technologies, R&S technologies in agriculture. So the adoption is a key in what impact can ultimately develop. Illustrate an example of a pathway of transformation for a case of weeding robot to understand complexity of the story. But as we go along, also motivate methodologies that help us assessing such potential pathways, given the current situation of, well, not being able to observe much of that happening already, especially what we are interested in, what happens if this is adopted at larger scale. So technology adoption is about more than profitability. In a recent study here by Dessart et al. In the European review, they looked at the factors that determine sustainable farming, the adoption of sustainable farming practices, not robotics and sensing technologies, but sustainable farming practices in general. And they showed how important behavioral factors are. Behavioral factors like dispositional ones that say something about the propensity of a person to behave a certain way. It's affected by environmental concerns, moral concerns, the tolerance to risk. This person might have specific objectives associated with farming, also away from maximizing profit. What matters are also social factors, interaction between persons, norms that exist. I'm doing things because my neighbor likes me to do that this way. But then there are also cognitive factors, which might come closer to what we traditionally think would matter for the adoption, like the perceived costs and benefits of a practice or a new technology. It's still perceived, so it might not really reflect what's in reality. It might depend on my social interaction and other things. So these factors determine a complex approach, a complex situation when we now confront this with a specific technology and ask ourselves, so what is the probability that this will be adopted by a certain farm, by many farms, where and how? Actually, the evidence, the empirical evidence in studies on technology adoption is abundant. That's a topic that economists have been working with for a long time. So they ask questions, or they're typically interested, how can policy, how can we intervene to help adopting technologies that are good for the environment, that are good for the income of farmers, and so on and so on. So they ask, how does a policy or activity of an extension service, how do different farm household characteristics, how do market conditions, and so on, how they determine the adoption of a technology at farm level. That this is really abundant shows this database that is currently built by Feisthauer and Schulz. They have already collected more than 13,800 studies. They want to use more than 1,000 of them for meta-analysis that I will briefly come to in a moment. And they have already 320 of them coded so they can actually do this statistical meta-analysis as already now and have some preliminary results. And these are preliminary results that you see here. So what you see here are confidence intervals of log odds ratios. So they say something about what factors in what way affect the probability to adopt a new technology. So these are measurable impacts. You see things like age, education, experience, farm size, market distance. These are measurable factors typically picked up in farm household surveys that could affect adoption. In the background, there might be this psychological constructs that we have seen on previous slide. So they might be affected, and working through them. But here these studies are mostly using then measurable variables. So then conditional, or these probabilities that they look at, they are conditional on these measurable determinants. And the confidence intervals now show the variation across these studies, but they also show whether they are generally more positively or negatively affecting the probabilities. And if we take just for example here, the access to capital is generally shown to be positively affecting the probability to adopt technologies like improved seeds or fertilizer, chemical fertilizer use. If we look at market distance, the higher the market distance, we would expect less commercialization, especially in a developing country context. And here you see the tendency to have a more negative impact. But you also see that it's varying depending on the technology considered and varying between the studies. We come back to that. So farm size, you see here, is a variable that's very often used in these studies. So we have a lot of numbers across different types of technologies for which we can look at the impact of farm size. And here we see it is really indeterminate overall, negative, positive, typically overlapping that point where it changes. So we cannot say really that farm size is clearly related to adoption probabilities here. Well, this sort of overview is telling us something about the relevance of measurable factors on adoption, but it doesn't really yet help in assessing robotics and sensing technologies. So most of these studies consider one or very few technologies in one or very few local or regional contexts. So that means we've also from the meta-analysis is not so easy. Well, the relevance of the context or the technology attributes. So context, farming system, agroecological zone, or technology attributes, chemical input saving, labor saving, risk reducing cannot be assessed by these studies. We might have a chance now to use the meta-analysis to put this in hindsight on top of it. So if we do manual coding of attributes and context variables based on the description of what we see in these studies, and then get the variance in terms of technological attributes and context variables into our meta-analysis, then we can learn and ask ourselves, so how do these attributes or the context affect adoption? So I recommend here the talk of Schulz, who goes deeper into it on this event. So then an alternative would also be to look at existing digital technologies only. So adoption studies that deal with more modern digital smart technologies. So here the literature is very limited. We have maybe between 40 and 60 studies used here in a current paper that's under review and led by Lin-Mei Shang. We also see that even in this case, the focus is again on farm and operator characteristics. So what you see up here, the farm characteristics and the operator characteristics, they have the longest bars to the right, which means they are included in the largest number of studies. Again, this are variables coming out of typical household surveys, and they allow us to then later move from the structure of the farms to the probability of adoption across a larger scale. But what you also see here for the first time are attributes of technology like complexity. Are their data safe? Can they be observed already? So they start appearing here, but are still only very limited in terms of the evidence. Well, one interesting thing we want to look at is again this farm size variable. So here you have again box plots with confidence intervals, but these are not log odds ratios, but instead standardized coefficients. However, for our purpose here, we can interpret them in the same way. We're looking at the impact of these variables on the probability to adopt now for digital technologies. And we look at the farm size. And here, the farm size is clearly positively affecting the adoption. So we are here with the box plot to the right of that zero line that determines whether we are positively or negatively affecting adoption. So the question is that already an indication that smarter technologies, where the farm size matters in the sense that it's more attractive for larger farms, or is that just here the specific small and not representative for our envisaged technologies collection of things that make it happen? Well, it will take a long time before we get more empirical evidence on farm level adoption of robotics and sensing technologies. So another way to deal with that issue is to work with choice experiments. So have hypothetical situations set up, hypothetical attributes of technologies, packages that are offered to the farmers, real farmers, or those that we are going to use here in experiments and ask these choice questions. And this is another method that allows to, assess something when it's not observable yet, as we have here in our case. Well, we talked a lot about adoption at farm level, but when we have more farms picking it up, then we quickly go into upscaling impact at larger regional scales. So what happens is that certain determinants might now change, or the determinants that we have identified at the farm level might now change depending on the overall level of diffusion of a new technology. So for example, the cost of the technology might go down by more and more people adopting it, yes, because we get economies of scale in the production. So it gets more and more attractive, and thereby creating additional incentive for the next ones to adopt. If we have certain markets that these new technologies are delivering to, the prices might change and also change again the attractiveness. There will be policymakers seeing the potential and maybe thinking about how to enable the uptake of these technologies by certain interventions, financial incentives or regulations. It matters what others do. As we already saw, social factors play a role. So the networks that exist between farms will matter for the speed and the spatial extension of uptake. So Lin-Mei Shang in her talk also at this event will talk about more about the connection of farm level with agent-based model as a tool to do these laboratory foresight studies, experiments, into sort of understanding how would adoption work at a larger scale. Interim keep here on the technology adoption before the last part of the talk. So we can keep that heterogeneity of farms, farm operators in context matters for R&S technology adoption. And that we know little at this point about the relevance of technology attributes for the adoption. However, we work with methodologies, start working with it that might actually get us there step by step. The uptake at larger scale diffusion depends on social interaction and institutional feedback. And to get this a little bit more concrete, we move now here to possible impact pathways. Actually, so far, we have not really talked much about impact. We have looked at adoption of new technologies, but the impact now depends on, obviously, the technology attributes, but also how many pick up the technology, what type of farms pick it up, what is the relative benefit in terms of economic and environmental outcomes. So what we see here is an impact pathway graph. We have the market share on the vertical axis. We have time on the horizontal axis. And then we have conventional technologies and sensing and robotics in gray and green. So when we now move along this curve here, this S type of curve, all the way up here, the pickup of the sensing and robotics technologies increases, and ideally we end up here at a market share of 100% or at some other market share where further adoption is not happening. So what matters for the adoption and in now here at larger scale is the context. Yeah, what production systems are we looking at? What is the farm structure in the region? What are norms and regulations, policies, but also cultural things that are happening? Adoption is driven by drivers, which could be population growth, land degradation, so environmental pressures that exist, pollution that really needs to be handled, and that then also has environmental and agricultural policies as a consequence, which lead to different benefits of technologies at farm level. We talked about mediators already in the sense that we have markets for inputs for the technology itself, but also for the outputs, that if more and more people pick up a new way of production, it will change by that already the conditions for the next that are still considering to pick it up. We have social networks that matter and so on. So the extent of uptake and the type of technology will then determine the outcomes. Now, in terms of economic and environmental indicators, yields play a role, resource use, pollution, landscape transformation. So measuring those and looking at them will determine what is the impact, what is the outcome here. To get this one step more concrete, let's look at the specific thing, an automated weeding robot. And the key here is that it may matter for some more than for others. So what we have here are farmed-in simulation results. So farm system simulator given us by Julia Heinrichs, which allows to generate production costs by detailed crop management resolution in there, production costs for different types of farms. So here it's production costs depending on the farm plot, distance, or the farm plot size. But what really interests us most is the difference between organic and conventional. So on the left-hand side, you have the current situation where the organic have to do manual in-row weeding. They cannot use herbicides. And compared to the conventional, their production costs per hectare are really way higher. But if you go to the right-hand side now, then you see that in the case they do not need manual weeding, so this is taking now the cost of manual weeding out of both production systems here, then organic and conventional get closer to each other quite a bit. Please observe here also the scale, which is lower than on the left side. So the organic drops down almost all the way in production costs to the conventional. So what does it mean? It means that the benefit, the attractiveness of an automated weeder obviously is much higher for an organic farm than for a conventional, at least as long as herbicides can still be used by the conventional. So now we return to this sort of impact graph and look at sort of two different possible pathways and what consequences it might have for the impacts of the technology adoption. So we have seen from the simple calculations before that it will be much more interesting for the organic farms to adopt an automated weeder for tuber crops that might come out here on the market. So the early adopters will be organic farming. What does it mean? Well, here we see the market share on the left-hand side of the automated weeders here, and the sustainability impact in green on the right-hand side. So organic farms, they have not used herbicides before. Their biodiversity footprint was quite good. So nothing really changes if they are adopting it, except that we get an increased carbon footprint. Why? Because labor, manual labor, is replaced by robots needing energy in producing the robots, but also in operating the robots. So we have an environmental damage, if you wish, if we only get so far here to this breaking point, where the question is asked, do the conventional farms also adopt? And something must happen for that. For example, the demand for organic produce goes up significantly because of developments, and conventional farms follow the price differential and the advantage on the output market. Policy might say, okay, hey, we have this weeding now, which works, the automated robot weeding. Let's not allow herbicide application anymore. Then suddenly things get really interesting for the so far conventional farmers as well. But it's really this additional incentive that would really determine the overall environmental impact. So if the uptake goes on, and now the formerly conventional farms pick up the automated weeding and do not use the herbicides anymore, then we get this increased biodiversity in conventional farming, or the effect on biodiversity through the drop in pesticide use, and overall performance on the environmental side goes up. So this is still a simple example, but it's sort of one context, one technology where we already see that it's not so straightforward to think, okay, because a weeding robot can do something good in our experiments on a field, it will also do good when it is adopted at market scale. It depends on how and who is picking up, where, in what context, and so on, and what speed. So it might be worthwhile to think about this more. To conclude, way too short here, the possibility. So to conclude, adoption and diffusion of robotics and sensing technologies in agriculture is a complex process. Heterogeneity, context, and dynamics matter. We have seen that in several contexts. Knowledge on possible transformation pathways really of robotics and sensing technologies is very limited. And we start thinking about this in terms of examples, but hopefully what you saw is that it might be useful to think about that more and more systematically, and also get informed by the technology developers. So where's the readiness, or what is the level of readiness of the next technologies, and what could that mean for transformation pathways in terms of timing and so on. But we also see in terms of analysis that it's really necessary to apply a methodological mix to assess potential of transformative impact of these technologies. We need to exploit existing studies, so generate new evidence based on existing studies by putting work in, and have sort of a second level exploitation of that data. We need to generate new empirical evidence through choice experiments or the first implementation of smart technologies. And we also need foresight tools, simulation-based tools that help us to understand what is really the importance of the different drivers and mediators in that uptake and diffusion at larger scales. And if we learn more, then yeah, we can contribute here to the sustainable food system, which is described and discussed here in an article by Herrero in Nature Food, worthwhile reading. Thank you very much for your attention, and I'm looking forward to discussion at the live event.